Okay. Yeah. Hi everyone. I'm Huiren. So I'm here today to talk about how to build your own real-time chat with no external dependencies. So it's gonna be more of like how you can eventually guide your LLM to code the application for you as well. So the goal of the presentation is to learn more about like manual important steps to prompt. So you learn about computational thinking and how to design your architecture and how to manage your trade-offs, right? Because in engineering, there's always a lot of trade-offs that we are constantly making for each decision, right? So things that I'm not going to be covering on is things like SDD or MCP workflows, all right? So we'll learn about how you're going to manually apply computational thinking, write some pseudocode, and then design the architecture and stuff like that. Right. So who here has heard about computational thinking before? Show of hands. Okay, a few. Yeah. So computational thinking, right? It's actually a generalized problem-solving technique using 4 steps. So it's not limited to just the computing field, right? Sometimes it's used in US application, right? So for me, I learned it in a module at NUS. It's called GT1031 by Dr. Leong. So it's quite a life-changing module. I think it's especially important with the advancement of LM technology that we learn computational thinking. So what exactly are the steps involved in computational thinking? So we have the first step is decomposition, which you want to break the problem down into smaller problems. Followed by pattern recognition. So you look for common patterns and stuff like that, or repeating patterns. Then followed by abstraction, where you remove the unnecessary details. And then you focus on the general modeling or interfaces. Right. And finally, we have the algorithm, which is actually to write like pseudocode. So not necessarily you have to write like TypeScript or any Golang code or stuff like that. So let's form a problem statement for us to solve. So this is kind of like a practice, like kata, where we try to exercise our brains a little. So we have a problem statement here, which is kind of like an ideal scenario where the problem statement is properly defined. So here comes the problem statement, right? How can I build a live web chat application without relying on external dependencies? So what I'm referring to is like WhatsApp or Messenger or IRC, right? Not a chatbot, and no external dependencies here refer to, refer to npm code dependencies, not dev dependencies. So like unit testing and stuff like that. So this is what I'm scoping out, and it's more of an exercise of basic exploration of a database. So here are some of the 3 potential features, right? Which is like real-time message receiving, real-time message sending, and then you also have message history. So we can decompose the problem, right? Which is live chat app. We decompose it down into 3 sub features, which is real-time message sending, real-time message receiving, message history. And then we can further decompose them down into specific parts, such as the UI, what is the message model you're going to send, how you're going to store the message, how is the networking carried out, right? So we can decompose them down into sub-problems like this, right? So for example, let's say you open a web application, the user is shown a UI, and then type message gets sent to everyone, right? How you receive messages, right? So these are like how you would decompose them now into all these certain parts. So this is kind of how I envision it to be, right? You have the chat log messages, and then you have the chat message input, right? So the specifics of like what I'm going to input is not defined yet. So let's say user A types a message. User A and B both sees the message. we don't know what is the networking tier yet because we haven't defined it. We also don't know what is the message model because we haven't defined that either. Right. So going further, we have like the UI, the message storage, and then the message model itself, right? We want to talk about like the payload format. How is the message gonna be sent? Is it gonna be sent in plain text? Is it gonna be sent in binary? Or how is it transmitted? Right. And then you have networking as well. Right. How do the clients discover each other? And how you're gonna handle disconnects from all this. So now we apply the pattern recognition, which is that we have the payload format, right? So there's multiple ways to do payload formats. We can go with binary data format and implement our own proprietary format. We could also go with a canonical data model, right? So if you read up terms like from the enterprise integration pattern, there's a book. It talks briefly about certain kind of patterns, and one of it is a independent common payload that can be consumed by everyone. So in short, it could be something like JSON, right? Message delivery, how are you gonna deliver the message? Could it be pops up, fan out, multiple subscribers with one publisher? Could it be peer mesh? Could it be reliable send format where you send and then you retry later on, right? And how are you gonna handle message storage, right? The patterns of ways which you can handle message storage is like many ways, right? We have peer mesh, we have centralized database, we have a hybrid model, and then we also have to consider the trade-offs, right? What is the latency versus the complexity, the server load versus the client complexity, the connectivity, and its privacy as well, right? So now we move on to the third step, which is to abstract the information, right? So we have the core data model. So this time I'm gonna decide on how I'm gonna choose it. So this time I'm gonna choose a canonical data format. I'm gonna go with something like message ID, sender, timestamp, message, right? And then we have a message state machine. We define client interfaces. Here we have something like, oh, let's say subscribe to the server, send message, or display. So these are the interfaces that we are defining here, right? And then we have the server interfaces where the server would then listen to stuff that is happening, store messages, retrieve messages, or broadcast to all the connected clients, right? And the transport itself, right? It could have state of its own. What is the send and receive behavior, right? So for the algorithm itself, I'm going to choose the greedy method. So there are many different types of algorithms out there, and they have different categories. So the greedy method usually works for some cases, right? And it's also not always the most ideal case which the greedy method would be useful. But we're gonna do a very simple exercise. So it's very simple. We're gonna choose a simple live architecture, right? So we're gonna go with client server using HTTP. We're gonna do functional correctness over scalability, right? So for the algorithm itself, we're gonna do pseudocode, right? As said earlier on, and it utilizes the abstract interfaces we have defined earlier on, right? So this is how it kind of looks like, right? You define these interfaces, and then you have the server that have certain other interfaces as well. So, sorry, there's also non-functional consideration as well. They are not within the scope of this talk, which is like authentication, cross request forgery, scalability, like how specific number of clients we need to handle. So let's take a quick. So everyone have any questions? Oh, okay. So I'm gonna go through. So there's a lot of text. How does that all translate into? Here's how it kind of looks like. right? You have the client browser, right? How you're gonna, it starts off by subscribing to the server, right? And then once you subscribe, you can start sending the message to the server. And then when the server receives messages, it broadcasts to all the clients. Client C can subscribe to the server, retrieve all the messages that has been sent to the server taskbar. And yeah, so that's how a client will connect to the server, right? And then we have the server architecture. It looks something like this, right? So you have the instance A, instance B, instance C, right? So let's say the instance try to store messages like that, right? And then thereafter, they can retrieve messages like this. And then when B stores a new message, you can retrieve, when they all retrieve, they get the consistent format, the consistent data that has been sent so far. So we want to talk a bit about polling, right? Because when we are handling multiple instances, not all the data has been broadcasted to the client. But how does the server knows that new data is in the database, right? So we can actually do a very simple method of doing this, right? Let's say you store messages, and then you retrieve fresh messages, right? So you have A, B, C, 1, 2, 3, and then nothing is happening. And then you retrieve fresh messages again, you get nothing because there's no new fresh messages since the last poll, right? But for B, since he hasn't received any messages before, he will now receive A, B, C, 1, 2, 3, which are the fresh messages that he has never seen, right? So storage is like we're gonna go work on a database, right? But modern databases are very complex, right? And database is basically a system that stores and manages your data in like different ways, like files in memory or across a network, right? So we're gonna go with writing a simple persistent flat file database, okay? So we apply the same concept, decomposition, pattern recognition, abstraction, and algorithm, right? So we decompose into different parts, right, of the problem, reading from existing data, right, persistence, and stuff like that. All these are the sub-problems, right? And then part of the patterns, we have different ways to read files, right? We can do log read, we can do fan-out reads, we can do fan-out writing, we can do write and forget, we can do cube writes, we can do log writes as well. Many different patterns available, right? And how we're going to store the message itself, there's also multiple ways, right? You could store it in memory, you can store it in a single file, you could store it in multiple files as well. And the message data itself, you can store it in different formats as well, right? It can be human readable, JSON, YAML, plain text, or it could be machine readable only, like binary, right? And then the data model, we're gonna follow what we said earlier on, right? The algorithm design itself, this is the algorithm that I chose, was to read and write human readable JSON data, right? So it does non-appended full override, right? It'll be a single file. And to handle scale, I'm going to do a simple write log that works most of the time. We'll go through the trade-offs that we are making here and what are the downsides of this design decision as well. Right. So we're not gonna write. We're not gonna log the read either. So it's gonna be unrestricted. So how does the algorithm work? I'm gonna check if the write log exists. What is the timestamp stored? Right. All these steps. Right. And then we're gonna go through the limitation of that design that we just showed just now. Right. Which is that we have race condition and also infinite waiting, which is your deadlocks, right? So you can face deadlocks as well because of how, well, not really deadlocks in a sense, but it's more of an infinite waiting, right? So this is how the database is going to look like. We're going to have the server software interact with the NodeJS API, which will interact with the operating systems, which then interacts with all these underlying files itself, right? So we have all this in our data format here. So how does the log write works? We're going to check for if the file exists, and then check the timestamp on the log file, and then how it reduces the overrides. It works like this. Is there a write log? Right. We check, and then okay, A says no write log. I'm gonna start writing. I'm gonna create a write log, and then B checks, is there a write log? Someone is writing, so B doesn't write. B waits for 100 milliseconds. And then once A is done, A would release their write log. And then B now has woken up. B is going to ask, is there a write log? No write log. So it creates its own write log, and then it writes. Once it finishes, it releases its write log. So while the race condition is when both of them at the exact same time checks if there's a write log. And then both of them start writing because there's no write log at that moment, right? And then there's also infinite waiting. A says, is there a write log? And then starts writing. B checks if there's a write log, so it sleeps. Okay, A is done. Okay, and then A now receives a new write order before B woke up. And then A says, is there a write log? And then it starts writing record 3. And then B is like, oh, I just woke up. Is there a write log? No, someone is writing. A is writing again. So that's how you can get into an infinite wait for B, right? Potentially. So these are the limitations of the algorithm that I've chosen. So these are the servers that are calling the Node.js APIs.
It's a server process.
Yeah, it's your Node server process.
So this is just to have a writer process. You send all the messages to the writer process, and then the writer will decide how to talk about it.
Sorry, as in
Have a single writer process. They will do the writing.
Yeah, so there's
with the writer process, and then you write.
Yeah, so there is another way to design the algorithm is that you have a separate software that manages the queue itself. So that will be your log queues, right? This is not the queue system that we are going for. So we are doing a more simple one, which is just log writes without queuing. So there's no queuing. The algorithm you describe would have a separate software that handles the queuing of the writes. So that's a different algorithm design, which is also a valid one. But I did not choose that design. Right? I choose with this flawed design instead. Yeah, so this is all intentional as well to showcase the limitations of this algorithm.
Can you share me the advantage of this?
Yeah, so the advantage of it is that it's very simple, right? So that is the main advantage of it, right? And you have a kind of you don't need a queue process because if you're dealing with a queue, right? Now you have another problem that you need to manage, right? What about the persistence of the queue? How is the queue prioritized? How are the writes going to be like? So it's a different whole set of problems that you have to design for. Whereas this is more of a simple, more of a straightforward approach. It reduces some overrides, but not all. Yeah. So the chance of you, if you're doing it at a very, very big scale, like a huge scale, the chance of you writing is possible for overrides to happen. But if you're doing, let's say, 3 or 4 instances of server, probably not. So that is good enough, right? The design is good enough to handle a small set of node instances. Yeah. So it's a simple targeted approach for a small scale problem. As we scale larger, right, our algorithm will need to evolve. And that's when we will have to start considering, hey, maybe we want to consider doing a queue system to queue the writes accordingly. All right. So this is how it kind of looks like. And then the parts we are building is the web UI, the file server, the file and API server, and then you have the storage server that we're also writing. So how we're gonna go about building that is now that we've done our pseudocode algorithm, we've done our design algorithm, we want to define other specific structure and then write our prompts, right? So our message structure goes like this, right? There's an author, there's a message, and then a timestamp, right? So there are things that are visible, right? Your username, your message, and timestamp. There are things that are invisible on the other hand, which is how can I uniquely identify which was the last message sent, right? That was picked up by the server. So if you recall polling, we talked about polling earlier on, where we poll from the server, right? How do we know that we have not read a certain message yet? So we do need a unique way of identifying a message as well, right? So we have the web and file server as well, which is to serve static content to the client. We're gonna have API endpoints. We're gonna define these API endpoints, right? Send message, server send events, and then a catch-all that serves static content from a specific folder. Right. So we have HTML, CSS, and JavaScript as our client content. Right. It's gonna connect with the API endpoints listed earlier on here, and then we're gonna send data to the API endpoints. So for our message storage, it's gonna be flat file, human readable, larger file size, just a single file, right? But of course, it's in JSON, right? So it's gonna require marshalling, right? So marshalling comes with its own downside as well. It can be resource intensive when you're doing JSON marshalling, right? So we've done that, and then we're gonna show a quick demo of how that looks like. So down here I have a how do I zoom in again? Control Command plus, right? This Command Shift plus.
I think it is control stroke.
This.
Oh.
Okay. So I'm gonna start the server. It's running on Node.js, right? So I'm gonna start my writing like this. So it's gonna run. I'm gonna run 2 instances of the server. So it's gonna look like this. It's gonna be on port 3000, right? And then down here, I'm gonna run another instance of the server. On 3001, right? So these are 2 separate server instances, right? So these are completely 2 different server instances, right? You can see I'm not faking it, right? I started out a different process altogether. So anyone wants to volunteer their name? No? Oh, John? Okay. John. Okay. So John, what would you like to say?
Hello world.
Hello world? Okay. So when you send a message here, right, on 3001, you also can see that the message got received, even though it's a different server or to a different server process, right? And then when we view the message itself, we can see that the data has been appended down here, right? So whenever you send a message, the server is gonna poll, right? Every few milliseconds, it's gonna poll and then check, hey, this message, I haven't seen it yet, right? Another thing you have noticed is that it receives the So let's try something. We can even do this, right? And then we save this. Of course, we change the ID, right? Now it's 2, 1 off. And then you see here, it's a new message, right? New message on all of them. So essentially, the server processes is gonna hold all of it, and then they'll receive all of that, right? So, although very much I want to show the prompts, I don't think I have time. So, so I'm just gonna go through like some tips, very short tips on how you can structure your prompts. There is a full article later on that I'll share on, right? So the main biggest takeaway is that you can break down your problems using computational thinking and structure it such that, and design your algorithm, design your architecture so that the LM is able to understand what you want, right? Because if you're saying, design me a website, it's a very broad, problem, right? Designing me a website is a very broad problem. So you want to break down the problem into steps so that the LM knows what exactly you want, right? So of course, don't just say like just code it for me, right? And this is an example of how I'll write a prompt, right? Task that needs to be fulfilled, example of task naming convention I want to use. So you want to give examples so that you can follow, right? Example of how I want to mock and stuff like that, right? So unfortunately, there is no time for me to go through all of that, but I've written an article that covers everything you need to know about. It's a 30 minutes article to read through how you can do reusable prompt files. So in GitHub Copilot, you have reusable prompt files and you have repository level instructions as well, right? So these are things that will be useful that we'll go into the specific examples of how I iterated through the prompts and what was the output, how I do code review. So whenever the prompt result comes out, you need to review the code, and how you review the code, what did I catch, what went wrong, and eventually how you adjust it. Right. So this is a 30 minutes read. So yeah. Thank you everyone. Well, any questions? Any questions? Yeah.
For Huiren, as a beginner, first developer, what's your recommendation for starting?
Recommendation towards
First starting by working on basic real-time applications using which programming language?
so I think generally it's better to write as a starter. You want to write pseudo code rather than a specific language code, because you want to list out the exact step that you want it to take, right? Because pseudo code can be translated into different languages as well. So the most fundamental thing that you might want to learn is how to write the pseudo code, right? Like where was the example? This, right? So something like this. This is your pseudo code, right? So you do a, so this is like a if statement, right? And then what are the conditions, the conditional flows and stuff like that. And then to answer your second part of the question about real-time messaging, real-time applications are, there's a lot of ways to handle near real-time applications, right? So there's a lot of already known algorithms or patterns rather, right? So patterns could be things like polling. Patterns could be like things like even you want to use WebSocket, you can do that. You can use queues as well, right? You can do publisher subscribers and stuff like that. Different patterns out there, right? So you need to know like a lot of different sets of patterns, right? And these patterns are not tied to any languages either, if that makes sense, because these patterns apply to a lot of different kind of programming languages as well, right? So start off with writing like pseudocode, and then read up on things like the patterns and algorithms. There are also useful books like SICP, one of the most useful books out there, Structured Interpretation of Computer Programs. You can look it up as well. It's free. You can read it on MIT's website. It's free to read. So you can read the book on the website. This one, right? And of course, there's a lot of catch to SICP as well, right? You need to know mathematics quite well, I think. Like it covers things on like Newton's method, right? And Pascal's triangle and stuff like that, all your mathematical stuff as well, right? So SICP teaches you different algorithms as well. Yeah, so you can read parts of it. You don't have to read everything as a starter. Yeah, pseudocode, SICP, and stuff like that are very helpful, I feel. Yeah, anyone? Yeah.
Even the public cloud, they have an attribution house developer put their codes into the services. I don't know, AWS can use that functions. You can use watch or there's an SMS where you can do outside. Do you recommend to use public cloud services which you can put or you start from?
I think a lot of it depends on what problem you're trying to solve, right? So it goes back to computational thinking. The first step of what is the problem, right? And then you want to break down what are the exact steps, what are the exact problems you're looking at, right? And then from there, you see what is the technological fit afterwards, because that is the pattern recognition part, right? Where AWS might be helpful, but maybe based on your problem requirement, maybe it's an overkill. So you want to go for a more simple design first, right? It really depends on what is the requirement, what you want, what is the scale, because at every level of the scale, right? Because this scale that I'm doing right now, right? When you only have a few instances of servers, the write log works well enough. But if we were to scale up the applications to thousands or maybe even millions of users, that is a different scale of complexity that we need to deal with, right? So ultimately, the algorithm and the platforms you use and stuff all are very nuanced to what problem you're trying to solve. Yeah, I think maybe later on, you want to talk to me more specifically about it, then I can help you understand. Yeah. Okay.
Thanks, Huiren. Huiren was moving here.